So, in this chapter, we'll look at our past energy uses and where our energies come from, how much energy we use today, and where does it come from, and hopefully where our energy will come in the future. Okay, so this is a overview of our past and present and future energy use. So let's get with it. So we'll look at the energy use of humanity throughout history, current energy distribution, uh, and so on. And we'll also look at a model, Hubert model for resource utilization. So for example, how energy source is discovered, its use grows, and then ultimately, once it's depleted, how the energy dies, goes out of our portfolio. All right. Um, so here's a graph that shows you our energy needs. Now, if you were back in, let's say, a thousand years ago, well, back in the hunter and gatherer days, what you need is about 100 joules per second to run your body. Okay. And if that's all you need, that's your energy needs. Okay, so once you learn to use fire, um, once humans learn to use fire, you learn to cook your food and stuff and things like that. And then your food had a higher energy density. Okay, so uh, uh, so even though you need 100 joules per second when you cook your food, so let's say you start off with raw food at 200 joules. When you cook it, well, so you're cooking it and the energy density is increasing. Anyway, you start using um, more energy. Okay, now let's jump down to today in the US. Uh, so currently we are using um, 12,000 watts of energy, well, energy at the rate of 12,000 watts. That's 12,000 joules per second. So imagine this, just to live, um, for food and all that, you need 100 joules per second, but we are using 12,000 joules per second, 120 times the energy needs just to sustain ourselves. So imagine if every person on the planet was using energy at that rate, that would be totally unsustainable. All right. Okay, so where does the primary energy source in the U.S. come from? So here's a graph over the past 200 years. You can see that uh, wood was used back in the early 1800s. That was the only source of energy besides sunlight, and that use has been very steady. Um, and well, wood is used minimally anyway. Okay, back in the 1800s, then we discovered coal, and you see the use of coal was growing exponentially. And we'll look at these models in the Hubert model. Okay. And then in the late 1800s, oil was discovered, and once we learned to use, well, oil, we started using it. We learned techniques of extracting it and all. The use of oil exploded, and again, this is an exponential growth. And then natural gas, um, and in the 50s to 70s, we learned to harness nuclear energy, and we started building nuclear power plants, and this nuclear energy went up. Use of nuclear energy went up. Now, this is nuclear energy has is doesn't cause global warming, and so this is a um, good energy source. Unfortunately, we haven't built any more nuclear plants in the recent past. Mm, and so the the use of nuclear energy has leveled off. Mm. All right. So anyway, so this is so this graph shows you where we get our primary energy from, and you can see most of our energy comes from fossil fuel sources: petroleum, natural gas, and coal. You know, and as we've seen before, 80% of our energy comes from there. And these fuels, the use of these fuels increases CO2 level in the atmosphere, which causes global warming. So that's the problem we're trying to fix. Okay, so again, this just details what we said uh, before. So wood, the primary U.S. energy source was wood until late 1800s. Coal from 1800s to about 1950. Petroleum since 1950 is the main source. Okay. Now here's a very interesting graph. What this graph shows you is energy use per capita, that is energy use per person, and GDP per capita. Now, here's the deal. So you can see that the richer the country, the more the energy use. Okay. So actually, it should be really stated like so. If you want to be rich, you need to have access to more energy. Without access to energy, you cannot become rich. It's as simple as that. So now there are other factors. So for instance, if you live in a cold country, you have to use more energy. If you use more energy than if you're in a warmer country. Um, anyway, so here's a linear relationship, roughly linear relationship. Um, if you're twice as rich as somebody else, then you're using twice the amount of energy that the other person. Uh, so again, energy, without energy, nothing much can happen. Okay. So again, in the US, per capita power usage is 12,000 watts. That is, every citizen on the average is using 12,000 joules of energy per second. So, and another way to look at it is 120 100-watt bulbs are supporting each person's lifestyle in the US. That's 16 horsepower. Stated another way, what that means is 16 horses. Horsepower means one horse working. So 16 horses are pulling your lifestyle 24/7, 365 days a year. All right. So factors affecting energy use, the climate. So for instance, Norway is a cold country, and you need a lot of energy for heating needs. Population density. If you're a sparse big country like the United States, you need a lot of energy for transportation. And if you're an industrial, if your economy is dependent on manufacturing quite a bit, you need energy for industries. Okay. Now, it takes energy to produce energy. Well, what does that mean? So, for instance, if uh, let's talk about electricity produced from coal. Okay, so electricity is a useful form of energy, uh, and if you're producing electricity from coal, you've got to dig up coal from under earth. So that takes energy. You got to transport the coal to the power station, and then you burn coal, and you burn coal, and from the heat you produce electricity. So all this essentially, when you burn coal and release 3 joules of energy, you produce 1 joule of electricity. So, for instance, it takes 3 joules of heat from coal, natural gas, or nuclear fission to produce 1 joule of electricity. So, to produce 1 joule of electricity, you essentially use 3 joules of coal. And again, we haven't factored in the digging of coal and all that. So, to produce 1 joule of useful energy, you need a 3 joules of primary source of energy. So, that's what we mean by energy to produce, energy. So now why do we do this? We do this because electricity is a more convenient and useful form of energy. You can't do everything you want to do with heat alone. Okay. Now here's another thing. So it takes about 8 calories of energy to produce 1 calorie of food. Okay. So to produce food, uh, producing food is an expensive proposition. But of course we have to eat, and so we are willing to do that. But now, for instance, if we had to use 8 joules of heat to produce 1 joule of electricity, maybe we wouldn't produce as much electricity. So that's the point. Okay, so now why do we bring this up? So the question is, fundamental question should be, what is the cost of energy to produce 1 joule? So when you're looking at renewable technologies of the future, if you're looking at any new source of energy in the future, it shouldn't, if it took two, let's say 20 joules to produce 1 joule of electricity, then I mean you certainly wouldn't look at that technology. Okay, so that's the point. All right. So we'll look at annual energy use in the United States. This is a pretty busy chart, so I'll just show you. Uh, um, um, I'll just show you a couple of things about here. Now, here's something that you need term you need to be familiar with. Um, and there's a unit called a quad for energy. That's a quadrillion BTU of energy. And let me write down. Uh, a quad equal to about uh, 10 to the power 15 BTU, and which is roughly 10 to the power 18 joules of energy. Okay. So the world uses roughly 500 quads of energy annually, and the US uses 100 quad, about 20% of the world energy use. Okay. So the United States uses about 95 quads. Okay, and here's where we get all the energy from. Okay, so this is what it lists our energy source. So 35 quads come from petroleum, 4 quads from biomass, 20 quads from coal, 24, 23 quads from natural gas, and you see renewable sources are quite small. Okay, nuclear energy provides about 9 quads, and remember, nuclear energy has operationally zero carbon footprint. Okay, so we get 100 quads from these sources, and here's the deal: out of the 100 quads, 40 quads is usable energy. That means that 40 quads is turning motors, transport, um, getting your cars up to speed, and so on. And 60 quads is rejected to the environment. That's wasted energy as heat and so on. Okay. So what we are saying is, out of every $100, $40 is what's actually spent, and $60 is wasted as heat, and there's nothing we can do about it. Okay, so with the current when you use heat engines, there's no escaping that. So for instance, let's look at this petroleum, use of petroleum. Petroleum is mostly used for transportation. Okay, so out of the 35 quads of petroleum, 27 quads is used for transportation. Okay, and about 8 quads is used in for industrial needs. So, on the transportation of the 27 quads, so out of the 27 quads, 7 quads turns is turned into motion, and 20 quads is dumped wasted as heat. Okay, so you can see that 27 and 7, your vehicles are only about 20% efficient. Anyway, so here this chart shows you the primary energy sources, the wasted energy, and what you actually get out of the energy. So per capita primary energy use in the US, this is, so we're looking at numbers typically in the north. So we said that uh, in the US, the average person uses 12,000 joules per second. Okay, or 12,000 watts. That's the rate at which energy is being used by an average person. Okay, so here's where they are using gasoline for transportation, oil for heating, mostly up north, and air conditioning in the south, electricity, and electricity. Okay, this accounts for 5,000 watts. Okay, and the other 7,000 watts is the remainder is used by industry, business, government, etc. On your behalf. Okay, so that's where your energy needs. That's where your energy budget goes. So why are we talking about all this? So we're talking about all this because in the future, uh, well, we'll model how many people will be there on the planet and what will be their energy needs and where are we going to get this energy from. So we'll be trying to answer questions such as, is it possible for the world to uh, function on just renewable sources? So those will be the big questions we'll try to answer.